I'm sorry, so lie and pretend that you're okay. Swear that you will stay. Keep trying for one day. Whoa, I'm sick of all these lies. Don't care if I capsize. It's not the life for me to hide. Don't wanna live a lie. Too many lows, too many highs. Too many things to criticize. So I leave it all behind. Don't wanna live a lie.
So you have written the notes about conservative field. Conservative field is a field in which work done is independent of the path. Non-conservative field is a field in which work done is depending on the path. Proof also I gave you yesterday, isn't it?
So non-conservative is independent.
What?
Non-conservative is independent.
Non-conservative depending on the path.
Okay, sir.
Example, friction. If you pull an object 1 meter along the floor, that energy lost. That energy lost. It won't be conserved. If you're pulling back, again you have to do the work, that again lost. But when you're lifting an object, you have done a work, energy stored. While it is coming back, same energy used. You understood?
Yes, sir.
Sir, the proof you gave that is conservative.
I gave you conservative. Conservative is independent of the path. That means whether you are taking an object this way, this way, this way, this way, this way, and bring here, or directly you're bringing here, it's same energy.
Okay.
But on a road, on a floor, if you're taking this way, on the floor, okay, a chair you're pulling along here. Okay, if you do here, work done, lost, heat energy lost. Here again lost, again lost. So depending on the path. Their energy not conserved. That is the reason. Clear?
Yes, sir.
But we are lifting in the air. Through the air, if you are doing, it will go like this. Here, 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 here. This energy we are storing, and directly if you are lifting, same energy. Because energy is not losing there. Next, work done due to a variable force.
Sir, what about non-conservative force?
It is depending on the path. Example, friction. Work done due to a variable force. Look here. Until now, in smaller classes, from smaller class onwards until today, we were discussing about work done is force and displacement in the direction of the force. But force we considered is taken as constant throughout the displacement. For example, an object, we exerted a force of 10 Newton and this object is displaced 10 meter. That means just 10 Newton will not bring it here. We should keep on exerting the force 10 Newton until it reaches this point. Just 10 Newton, it will just move and stop. If you want to move it 10 meter, constantly you should apply this 10 Newton and bring here. This is the meaning of it. So W is equal to Fs cos theta. It means this F remains constant throughout the displacement. But most of the real situation in our life, this force is not remaining constant. For example, suppose this is Earth. At a x distance x from the surface of the Earth, if we keep a small object, force acting will be G m1 m2 by r square. Here m1 is the mass of the earth, me. Mass of the object I am taking m divided by distance is x squared. You know this gravitational force. Agreed?
Yes, sir.
So this is the force acting on this object towards the center of the earth's attraction. At infinity, if you are taking the object, see x value become infinity. Infinity means 1 by 0. 1 by 0 means 0 will go to numerator. So this will be, force will be 0. For example, F is equal to G M E M. X is suppose infinity. From here to here, X is infinity means 1 by 0. 0 will go to numerator. Whole thing will be 0. On the surface of the earth, if you are taking, suppose 1 kilo body, if you are taking, substitute here, G 6.6 into 10 to the power minus 11. Mass of the earth is 6 into 10 to the power 24. Mass of the body is say 1 kilogram and distance is this radius of the earth. That means on the surface, that is 6,400 kilometer. If it is like that, if you calculate the force on the surface of the earth, it will come 9.8 Newton. This calculation we'll study later. Now see, infinity it is 0. On the surface, force is 9.8. Suppose you are bringing an object from infinity to, this is 1 kilo object from infinity to here. Force is, W is equal to force into displacement cos theta. Anyway, theta 0 because force and displacement are same direction. Force, now S we can calculate. How can we calculate X? Infinity, from center we have to calculate. Infinity minus 6,400. Then you will get distance from here to here. This distance you will get S. But which force you will substitute here? Will you substitute 0 or 9.8? This is a question. If it is uniformly increasing, say 1, 2, 3, 4 equally increasing, you can take average. But here square the factor change is coming. Then you cannot take the average. Then which force you will substitute? That's the question here. This is the main challenge in work done due to variable force. That means every instant this force keeps changing. So here we have to make a situation that while you are calculating work, force must be constant. How much displacement you are making, in that displacement force must be constant. Okay, now two methods we have. One method, graphical method. Second method, integration method. Let us see what is this graphical method first, then you will come to integration method. Okay, look here. Graphical method, I am going to plot a graph. Okay, a large graph I am going to plot. Before that, let me explain this part also. Look, this is the surface of the earth. Let us assume this way the concept. Very, very, very important area, okay? Because hereafter we are discussing only with the variable force in your higher classes. Suppose here to here, we are making a flat system, okay? Flat. That is, this is first floor, ground floor, first floor, second floor, third floor, fourth floor. Like that, I am making until infinity. Until infinity, we are making a flat system. Suppose you are living in this point. So earth will attract your body in downward. Suppose your weight is 60 kilo. Then force acting onto you 600 Newton, isn't it? If you go from first floor to second floor or ground floor to first floor, will your weight change? Suppose you are going from this floor to this floor, straight away in a lift. Will your weight change?
Yes, sir.
Will your weight change? How much it will change? Can you tell me?
No,
Suppose down floor, your weight is 60 kilogram. You are going and measuring on the upper floor. And will it be 70 kilogram?
No.
There won't be any change, right? There won't be any change. But just like you said, there is a minor change which we cannot even notice it. Even we cannot measure with the device. Such a minute change will be there, isn't it?
Yes, sir.
So this distance may be, when we consider this distance may be 4 meters, because from this ground floor to first floor, if I'm going, distance may be 10 meters. So this 10 meter we are considering as dx. This is the concept of dx. Dx means delta x tends to 0. We call it dx. Delta x means small displacement. That means concept dx has no specific value. It is a relative value. Is it clear? Dx tends to
Yes, sir.
0.
Yes, sir.
Dx tends to 0 and infinity are relative values. That's what I'm telling you. Say, for example, for an elephant, 1 kilogram body is tends to 0. A small body. Elephant will just take it and throw. But for a small fly, butterfly, if you are trying to lift it, it is very heavy. For that infinite, like a mountain it feels. So that same 1 kilo has two different concepts. Is it clear? For an elephant, it is tends to 0. For butterfly, it's infinity. So same ideas here also we have to see coming. So here, this 4 meter, that weight has no change at all. There is a change, but we are unable to notice it. Such cases, we can say dx, okay, delta x tends to 0. For a distance of dx, force remains constant. This is a statement I am going to use. So you should know what is the meaning of it, okay? Right. So here, from the ground floor to first floor when you moved, okay, then your weight remains same. That means mg or force acting to the floor ground remains same. That means that distance for which the force remains constant, you assume as dx. That means delta x tends to 0. Did you understand?
Yes, sir.
So here 6 meter when we are talking about, it's not that 6 meter. So when I'm saying delta x tends to 0 or dx tends to 0, does not mean it is going to exactly 0. Compared to the total distance to be covered, that distance did not make any effect over there. Such a distance as we call tends to 0. For example, I'm telling you I'm going to walk from here to the school around 3 kilometers. Then I walked around that near DPS I reached, and I said, see, 2 kilometers I already walked. Then he said, oh, sir, in this hot sun is walking 2 kilometers towards the school, you may say. But same statement I am telling the different manner. I am going from here to my house in India and same 2 kilometers I walked. You will say, sir is mad. Because how 2 kilometers make a distance to India? So that 2 kilometers different views. First case, it was a very large distance. Second case, it tends to 0 because that did not make any effect on my travel. So this is the idea when I am telling dx tends to 0. Don't think it is 0 or it is near to 0. Sometimes it may be 1 kilometer or 2 kilometers also. When we consider this building system, even if you go to 10th floor also, maybe 100 meter height, your weight is not going to change.
So, sir, D is distance, right?
D is the displacement or distance covered.
Okay.
Okay. So how long the distance covered for which force remains constant, that we are assuming as tends to 0. Okay. So this particular displacement force should remain constant. This is an assumption we are going to make here. Okay. You understood?
Yes, sir.
But, now just imagine you are calculating work from, you walked from first floor to ground floor to first floor. You calculated work. So your weight is mg or F, we can say, into distance of ground floor to first floor. Multiply. You will get work done in this region. That is dW. Now we are going to second floor to third floor. Again, force remains constant, right? Isn't it?
Yes, sir.
Again, you calculated dW. dW means small amount of work. We want to calculate work from surface of the earth to infinity. Since force is largely changing, we are unable to calculate like that. So what I'm going to do, I'm going to calculate from ground floor to first floor. Energy I calculated. Keep that measurement with you. Again, next floor, I went. You calculate. Again, next floor, you went. dW. So even though year to year there may not be change, but when you go from here to here, there is a large change in dW, right? Isn't it?
Yes.
dW value will not be same here. Here, if it is 10 joule, Here it may be almost 0.0001 joule because force is almost 0. Am I right? So try to understand, even though it is negligibly small, when you go to very large distances, this dW value keep on changing into smaller values.
Sir,
Clear?
force is constant here.
Force is constant only for small distance, not for
Ah,
large distance. You got it? Hey, look
yes,
here.
sir. Yes, sir.
It is going from ground floor to first floor. Then your weight may be 600. You are traveling 10 meters. So work done is 6,000 joules, for example. But here to here, when you travel, will your weight will be 6 kilo, 600. Will your weight will be 60 gram? I mean 600 Newton.
No, sir. It will change.
So it will be very small because gravity is very small, right?
Yes, sir.
Then your weight may be. Mass will not change, but weight will be very small.
Yes, sir.
Your mass is 60 into 10 weight. So 600 Newton here. But when you reach here, your mass will be same. But gravity is, for example, 0.0001. Imagine, very small gravity. That means 0.006 something weight will come here. Then you are making a displacement. So will this dW and this dW are same?
No, sir.
No. This we can calculate for this small displacement, force constant. So I calculated dW here. Similarly, for this variation, force is constant. So this dW I calculated. But this dW and this dW are not same values. This is very small, isn't it?
Yes, sir.
But the changes are gradual. We can't even see the change. Very small changes only will come. So this case we can say dW is equal to F dx cos theta. F means force. Dx is a small displacement. So if you want to calculate this small amount of work done, for dx distance, F should be constant. This is the condition. Now if you are going to calculate manually, look, dW here, dW here, dW here, like that. Every floor we have to calculate. Suppose here you are getting 10. Next floor may be 9.99999. Next floor again maybe, next floor to third to fourth, 99999, like that. Then 99. See, almost that small change will come. And if you add this plus, this plus, this plus, this plus, this plus, all this if you add, you will get total work done, isn't it?
Yes, sir.
But practically,
Yes,
is it possible? Adding little. How we will add? It will take ages to finish the work. For this, we are making another method. You see now what is the logic we are going to apply here. Okay. Here I am going to make a graph. This is from the center of the earth. It is starting. Surface of the earth will start. This is the x-axis. This is distance from the surface of the earth. This is the force. So on the surface of the earth, force is say 9.8 for 1 Newton force. Now graph if you plot, see force will not, almost very minute change only will come, right? Here I am marking 100 kilometer, 200 kilometer, 300 kilometer, 400 kilometer. See kilometer distance I am marking here. 500 kilometer, 600 kilometer, 700 kilometer, because actually 1 meter, 2 meter, 3 meter I cannot plot because we need very big graph. We cannot plot it in a paper. Is it clear? See, earth I marked, such a big earth, 6,400 kilometer I brought into a very small scale. See, if I'm marking 2 points, 1 point here, 1 point here, do you think distance will be 1 millimeter on this
No,
figure?
sir.
That will be very large, right? 1,200 kilometer maybe. This may be Jeddah, this may be Riyadh. Such a large distance. It look curved because it's small version. Similarly, graph also, real graph will be very large. We are bringing it to a paper. So actually that variation from year 2, that's what, first floor to 10th floor, if you go, you won't see the variation. So graph look like straight line. But actually graph is slightly bending. So in the graph, we can show like this only, you see, like this, slow, like this it will go. Slowly, slowly it will change. Finally, it will meet at infinity. That's what, see, I'm not touching here. This is parallel to the x-axis. It will become 0 only at infinity. Graph will be like this. Now in between, you assume a small point. 200 kilometer. 200 kilometer, if you are calculating force will remain this one. See, from the graph you
Sir,
can get it.
infinity also the mass will still be there, right?
Mass will be there. I'm talking about force.
Okay, sir. Thank you.
Okay. Now you see 220 kilometer traveled. 220 kilometer we are considering here. You see, this is 220. Same force will come, right? See, 220 also if you're marking, you will get same force, right? That variation you won't see. Am I right?
Yes, sir.
Now look here, area under this graph. See, area under this portion. This is A, B, C, D. Area of this portion if you are taking length into width. Length how much? Here, what is the force? Maybe 8, for example, 8 Newton. So force is 8 Newton into dx is how much? This dx, right? That means 20 kilometer. 20 kilometer. You understand?
Yes, sir.
That will give you dw of this region. If it is like that, here to here you calculate dw, here to here calculate dw, here to here calculate dw. See, area keep reducing. Calculate dw, area, you can see that area keep reducing. But each area will give you small values of dw. If you're adding the entire area, you will get total work, right?
Yes, sir.
Yes, sir.
So this is the concept. So this is what we are telling. That means if force is variable force, what we can do, make a graph, okay, in the scale which is possible for you, okay, make a graph. So when you draw in a paper, usually it comes like this, a graph, and calculate area under the graph. That will give you work done for variable force. You understood?
Yes.
But in integration, maths, now plotting this graph, okay, and calculating area is not that easy. Therefore, integration brought one new idea. Integration means maths, branch of maths. They said same answer we can get if you are using this formula. X to the power n dx is equal to x to the power n plus 1. If the distance variation from the object, from the initial point is this, then this formula if you apply, that answer and area under the graph is found to be same. For this, there is a proof that you will study in maths, others just by heart, by your students. Okay? This formula if you are applying, if the distance variation is based on this formula, okay, then area under the graph, this formula if you apply, answer will be same.
So
Now I
what
will show
symbol
you.
is to the left of xn?
This is called integration. This symbol shows integration. Integration means adding dw, small component. The process of adding this small component until final initial point to final point. That's called integration. Is it clear?
Okay, sir.
This symbol shows we are going to add this small components. Clear?
Yes, sir.
And we have to show limit also from where to where. That means
So
from
what
the
is x
center,
here?
distance covered. X keep on changing.
Yes, sir.
No. So initial point is how much? This is R is the initial point. Final point infinity. That we have to mark here. R to infinity we are going to add small component of f dx. See, f dx means small amount of work. This one if you keep on adding you will get total work. Now how to use this formula, that also I'll explain to you. Okay, listen. Did you understand this concept?
Yes,
sir.
we understand.
Now you see how we are going to apply integration. First you understood graph. How to plot a graph you understood. Now integration I will show you how to apply. Okay, look. This all again you will study in detail. Now I am giving a brief idea what is it. Suppose from the surface of the earth, okay, this is R. This is infinity. Okay. at a distance x, f is equal to, this is, f is equal, first you write the formula of f, that is g me m, g me m divided by x squared. Okay, this is m. Did you understand the force here? Any doubt?
No, sir.
No, sir.
I think you didn't get. See, here, this is Earth. Let us consider here a distance x. A distance x. Here I kept a force of mass m. Now force acting onto it. Force acting onto it is g MEM divided by x squared. This is a force acting onto it. And here we are making a small displacement dx first. Then formula dw is equal to f dx, because for this small displacement f remains constant. You understood the logic of it? Any doubt?
Yes, sir.
Oh.
No, sir.
The total work done from infinity to the surface of the earth r. Infinity from center, maximum distance is infinity, final distance you have to bring to this one. So infinity minus r will give you displacement. Okay, so w is equal to integral. You are starting from infinity and stopping a journey at r. Clear? Then f dx. This is actually, if you plot a graph, area under the graph is equal to this. Now w is equal to, substitute the formula, g MEM divided by x squared. This is a force, dx integral, time up, infinity to r. Okay, now w is equal to, already checked. Here, suppose this is earth. Okay, we are bringing an object. Don't write it just for example notes, I'll give later. Now at a distance, distance x from the center of the earth, let us imagine a small body of mass m, isn't it? This is
Yes,
f.
sir.
Now force acting on this object we have already studied, that is variable force, right? That's equal to, f is equal to g MEM divided by x squared here.
Yes, sir.
Okay, now you see. Now let us imagine this object is moved through a small distance dx, for which this force remains constant. For
Excuse me,
example,
sir.
1 meter, 1 meter, 100 meter, doesn't matter. Clear? A small distance dx for which force should be constant. Then we can calculate work done. dw is equal to f dx cos theta. Here theta,
No.
theta 0 means cos 0 1. So dw is equal to f dx. Any doubt in this?
No, sir. No, sir.
Now if you want total work done from infinity to the surface r, this distance is r. That means x value, initial value is infinity, final value is r. X is the distance from the center. So initially we are keeping the object at infinity, finally we are keeping the object at a distance r from the center. So we have to write total work done in bringing the object from infinity to a distance r from the center. This is the way it is representing. You see, total work done. That's called integration. Did you understand the meaning of that symbol?
Yes, sir.
Now f dx. This is the general formula. Now f is substitute. W is equal to integral infinity to r. F is substitute, that is g MEM divided by x squared dx. Okay. Look, W is equal to all constant we have to take outside, because constants cannot be added. Infinity to r, 1 by x squared dx. Okay. So in this, we know already integration formula I have told you. Integration x to the power n dx is equal to x to the power n plus 1 by n plus 1, isn't it? So here you see this x squared that we have to bring in this format now. W is equal to g MEM integration infinity to r. This x squared I am taking the numerator, x to the power minus 2 dx. Now we see this and this are same. This is, instead of n, I am marking here x to the power minus 2. And here minus 2 plus n, isn't it? Minus 2 plus 1 divided by minus 2 plus 1. That means answer will be x to the power minus 1 by minus 1 by x, isn't it? This will be the answer. So we can write W is equal to GMEM. This answer will be minus 1 by x. Now limit. This x can have two values. One value, initial value infinity, final value r. So we can write a W is equal to minus GMEM. First you have to give upper limit for infinity. That means 1 by x. Upper limit of x. Then lower limit infinity. Infinity 0. Therefore final answer will come W is equal to minus GMEM divided by x. This is the formula for work done in bringing an object from infinity to the surface. Did you understand?
Should we write this down?
Hmm?
So should we write this down?
What?
Should we copy this down?
No. This
Sir,
will
you get the last part.
This is an example I gave you. This is the way work done in bringing an object from one point to another point having variable force we have to approach. This is a method. Either you plot a graph or you can do integration method. So here I told you area under the graph if you are calculating, if you use integration, both will have same answer. I will show one more example, another example. Okay. Look, this all derivation will do later. Now for the time you understand what is it. Look, you know about spring, right? This spring.
Yes, sir.
In a normal spring, there is no energy in it. When you stretch a spring with a 10 Newton force, immediately that spring has a tendency to go back, isn't it?
Yes, sir.
Why? Equal and opposite restoring force develop within the spring. That means if the spring you stretch with the 10 Newton force, there is a restoring force developing that is minus 10 Newton.
Conservative field, sir.
Pardon?
Conservative field it is.
Conservative field, yeah. If you extend here 20 Newton, distance will be double, restoring force also will be double. This is the reason these muscle builders, that spring. If you little stretch, you don't have that much problem. But very large distance, if you just push it, your body will be, hands will be pulled back. You can see that. That means here we can say F is directly proportional to X. F is directly proportional to X. And F is equal to minus Kx. X increases. That means more you stretch, more restoring force will develop. Because for stretching more, you have to exert more force. And there is a formula, this before also in dimension I explained this part. F is proportional to X. And F is equal to minus Kx. K is called spring constant. K is equal to minus F by X. That means there are two springs. One spring when I exerted 1000 Newton, 1 meter it moved. Another spring just when I exerted 10 Newton, 1 meter moved. So this spring must be rigid spring because more force you have to exert for 1 Newton. Is it clear?
Yes, sir.
Is it clear?
Yes, sir.
Now
Yes, sir.
force while stretching a spring also not constant force, it's variable force. As the X increasing, more and more force you have to exert for stretching a spring. That means 1 centimeter, suppose you have given 1 Newton, then 2 centimeter to stretch you need 2 Newton. 3 centimeter stretch you have to give 3 Newton. So every stretch you have to give more and more force. See if I'm plotting a graph. First I will plot a graph for it. Okay. Initially spring 0, X is equal to 0. Now this spring we are stretching. We know as extension. Extension means X increases, force also increases. Clear? So for the graph will be like this, right? It's a uniform increase, not like Earth. In the case of Earth, it was inversely proportional to X squared. That's what that graph became like this. It became like this because x squared variation. But this is not like that. F is equal to kx. X increases, F also increases. That's what a straight line is coming here. Do you understand? Now,
Yes,
when
sir.
you make a
Yes, sir.
stretch, when you make a stretch of x distance, see, when you stretch it to a distance x, corresponding force developed is kx, isn't it? Agreed?
Yes, sir.
X distance when you stretch, corresponding force developed kx. Okay, now a very small displacement you consider. Here you cannot take 1 meter and out because already spring is very small. Spring is very small. In the case of Earth, distance to be covered is in kilometers and kilometers. There 10 meter also we can assume dx. But here can you say 10 kilometers dx?
No, sir.
No.
Spring is very small, right? So we can say 0.1 millimeter. Think like that.
Yes, sir.
That much stretch, force remains constant. Okay, so think a small distance dx, corresponding force remains constant. So area under this graph is dw is equal to f into dx. So we'll get work done for this small displacement. Like that, if we keep on adding the whole area under the graph OAB, for example, that is nothing but total work done.
Total work done.
Half into area, length is kx. Okay, this is x. Answer is half kx squared. Isn't it? This is the formula. This we obtained by area under the graph. Okay. Now I am going to apply integration. Let us see area under the graph integration comes same answer. I will show you that. Look, when we stress this x, force developed here is kx. Now by an external agent, I am giving the same force kx and making a small displacement dx. So we can write dw is equal to f dx. Small displacement. Total work done from x is equal to 0 to this x value. 0 to x. We can write here integration. Initially stretch was 0. Now stretch is x. Clear? F dx. Now w is equal to integration 0 to x. F is how much here? Kx. Kx dx. Now w is equal to k is constant, integration 0 to x, x dx. Power 1. Formula integration x to the power n dx. X to the power n plus 1 by n plus 1. Here instead of n we put 1. Okay. So this is also 1, this is also 1. So answer will be x squared by 2, isn't it? So we can write it w is equal to k. This factor will change into x squared by 2. You see, this answer and this answer are same. Any doubt?
No, sir.
So this is what I'm telling you. Area under variable force extension. Graph you plot, calculate area under the graph or apply integration this formula. Your answer will be same. This is the best proof for the time being.
Sir, we took k out because k is constant here, right?
Constant. Yes. Clear? So this is the
Sir,
basic
how did
idea.
you got that half kx square in the first case?
What?
How did you got half kx square in the
Area of
first
the
case?
area of the right triangle. Triangle is half into length into width.
Ah, right.
Length is x, width is kx.
Yes, I got it.
So this is what I'm telling you. So whenever you approach a situation, their force is variable and you want to calculate work, either you plot a graph and area under the graph you can calculate. Otherwise, apply integration formula, integration f dx. F the value will change. In the case of spring, F is equal to kx. In the case of earth, F is equal to g m1 m2 by r squared. In the case of electrostatic force, F is equal to k q1 q2 by r squared. Like that, depends on situation, F value will change, but method will remain same.
So the value of f will be given in the question, right?
Yes, it will be given. Okay. So now write work done due to a variable force. Now we are going to develop a general formula. Okay. Work done due to a variable force. Work done due to constant forces F into S. But work done due to variable force, integration f dx. It will come like that. Okay. Draw the graph. draw this graph. Just a random graph, anything. We are pushing with a variable force. A, B. A to B, you're pushing an object with a variable force. This side is force, this is displacement. These light lines are dotted lines, okay? It's a reference line. So initially, this is origin. Initially, this was at a distance x1. Now it is pushed to a distance of x2. In between, we are assuming a very small displacement. Very small displacement for which force remains constant. This is now F, this is dx. This is A, B, C, D. Area under the graph will give you dw is equal to F dx. Then area under the entire graph, B, C, D. W is equal to integral x1 to x2. Initially x1, finally x2. F dx. Okay, this is a graph. So only draw the graph now.
Sir, what is ABCD? Small letter ABCD.
Small letter ABCD, just marking ABCD for dx. Small displacement dx, area under that we are marking small letter ABCD. A this end, B this end, C this end, D this end. The displacement we call dx. Right now, let us consider a variable force. Let us consider a variable force acting on an object. Let us consider a variable force acting on an object, making a displacement from x1 to x2. Making a displacement from x1 to x2 as shown in the graph. Next paragraph. Let dx is a small displacement. Dx is a small displacement for which force remains constant. Dx is a small displacement for which force remains constant. Then area under the shaded region, see the shaded region, area under the shaded region, that is F dx. Area under the shaded region, that is F dx, is equal to dw. That is work done for small displacement dx, for which force remain constant. The importance of dx, force remains constant. So area under the shaded region ABCD gives F into dx. See, here to here this height F, this dx width. So F dx. That is work done for small displacement dx, for which force remains constant. Then total work done in displacing the object. Total work done in displacing the object from x1 to x2. Total work done in displacing the object from x1 to x2. Is integration, right? X1 to x2. Total work done in displacing the object from x1 to x2 can be written as W. That's equal to area under the graph capital A, B, C, D. A, B, C, D. Okay. That can be written as integral f dx x1 to x2. This is a general formula work. Now f only you have to substitute here. Working column, write the integration formula for your reference. This one, x to the power n plus 1 by n plus 1. This is the formula you have to apply, integration formula.
Sir, after writing the equation, what should we write, sir? After W is equal to that.
W is equal to integration x1 to x2 f dx.
After that, what we have to write, sir?
Nothing, finished. There is a work done. There's a formula for calculating work done for variable force. Clear? Then working column, you write this formula.
So this is for what? This formula? For integration of?
Integration formula.
So the denominator is n plus 1.
Yes. Okay. Next, energy. Next heading, energy. Energy can be defined as capacity of doing work. Capacity of doing work. So work and energy are same, effectively. If you're asked to calculate work, if you can calculate energy, if you're calculating energy, that is nothing but work. Capacity of doing work. SI unit is joule. SI unit is joule. Now potential energy. Potential energy. Basically, there are two types of energy, potential energy and kinetic energy. Potential energy means stored energy. Kinetic energy, that always causes motion. When a body is in motion, the energy possessed by it. How can we get a potential energy, stored energy? For example, if you take a spring and compress, that spring is under strain. That spring is under strain. Strain means giving a compression. Or it is stretching. Again, it is under strain. These cases, energy is stored. Or when you're lifting an object to a height of h, height of position, there you have an energy in a conservative field.
Select dams.
This is the potential energy. But if you push an object and causes motion, that will produce, then that work will convert into kinetic energy. These are the two types of energy, right? Potential energy. Potential energy can be defined as a stored energy. Potential energy can be defined as a stored energy when the system stored energy, when a work is done on a system, when a work is done on a system, in a conservative field, work is done on a system in a conservative field. And this energy is developed, when the object is under strain. I told you strain. Object is under strain or state of height. At a height, if you're lifting.
Strain under?
Under strain. Object is under strain or state of height. Now, gravitation, expression for gravitational potential energy for smaller heights, for which force remains constant. Gravitational potential, expression for gravitational potential energy for smaller height for which force remains constant. Look, here we have an object of mass m. Now the force acting onto it, F is equal to mg. Now how much amount of force you have to exert onto it to lift it with a constant velocity? mg. So we can say here, by exerting an equivalent opposite force, by an external agent, this object is lifted to a smaller height h, for which force remains constant. You understood why I'm specifying that part? If it is very large height, if you go, this method you cannot adapt. You have to go for integration method. Integration f dx. Is it clear?
Yes, sir. Yes, sir.
A derivation just before we have done from surface of the earth to infinity. That much height if you are going, you cannot just take mg into force into displacement. There you have to go for integration of f dx. Here we are considering only for smaller heights. That means I told you ground floor to first floor or second floor or third floor, for which force remains constant. Only to that extent this formula or this method is applicable. If it is to large extent, if you go, force will change, variable force will come into play, then this method you cannot adapt. You have to go for integration method or graphical method. Any doubt?
No, sir.
Now this object is lifted by exerting an equivalent opposite force. Okay, this object is lifted to a smaller height h, for which force remains constant. Then we can say W is equal to Fs cos theta. Or you can use this formula also because smaller height, right? dW is equal to F dx. This also can use. It's up to you. Now W is equal to F is how much? mg. S is h. Theta 0. Theta 0. So cos 0. Here theta 0 because both are in same direction displacement. Then W is equal to mgh. So this much work you have done, that much energy transferred from your body to that system. If an electrical lift is doing it, electric energy is converting into this energy. So who is the external agent? That energy will convert to the system and stored as a potential energy. So we have to say this work is developed as gravitational potential energy because we are doing work against gravitational force. Gravitational potential energy. Therefore, EP, gravitational potential energy, this is a symbol mgh. See, work only directly considered as H, potential energy. Any doubt?
No, sir.
Draw the diagram.
What is EP?
Draw the diagram. Huh?
EP.
Sir.
Potential energy.
Potential energy.
Draw the diagram. So here this work is calculated for smaller height. That's why integration is not coming. So here see F is mg, dx is here h, smaller height. But if it go to infinity, you have to go for integration method. Only diagram.
Sir, what about the equation?
Right. Let us consider an object of mass m. Let us consider an object of mass m. Next line. Let a force F, let the force F acting downward is mg. Then the force F acting downward is mg. F is equal to mg. Force acting downward is F is equal to mg. Next line. By exerting an equal and opposite force by an external agent. You have to specify by which force you have to calculating work. By exerting an equal and opposite force, bracket you can write F is equal to mg. By exerting an equal and opposite force, bracket F is equal to mg, comma, by an external agent. By an external agent. Let the object is lifted through a height. Let the object is displaced through a height h. Let the object is displaced through a height h, for which force remains constant.
Let the object
Is displaced through a height h, for which force remains constant. For which force remains constant. Then work done by the external agent. Then work done by the external agent is W is equal to Fs cos theta. Substitute. Then write this. Right here, W is equal to Fs cos theta, then continue. This work is developed as gravitational potential energy.
Yes.
sir.
Next, elastic potential energy in a stretched spring. Elastic potential energy. Elastic. That already we have done. Elastic potential energy in a stretched spring. Or they can ask compressed spring also, same answer will come. Elastic potential energy in a stretched spring. Just draw the diagram, that much time we will have. Here this is spring. Here x is equal to 0. Okay? No stretch now here. Draw the diagram. This concept you have discussed just before. This is 0 position, okay? Now same spring is stretched.
Sir, in the first diagram, the potential energy is 0.
0, no extension.
Okay.
Now it is stretching. Okay, by a force F. This is Kx. Now a restoring force will develop. This is minus Kx. Now by exerting an equivalent opposite force, let us make a small displacement dx. Therefore, theta is equal to 0. Up to here, you finished, then time up. It's 1 minute only, less than 1 minute.
The force V exert and the force exerted by the string will be cancelled here.
What?
The force V exert and the force exerted by the string, they don't get cancelled.
Now this force we are not applying, okay? Restoring forces F is equal to minus Kx, right?
Yes, sir.
To make a small displacement dx without acceleration, how much force you will apply in the opposite direction?
Kx.
Kx. Isn't it?
Yes, sir.
Okay, so it's time.